okay? Now, if anybody is unclear in the concept, what we're looking for, when the book uses distribution, they really mean density function, okay? Because that determines, that is the distribution, okay? So for continuous ones, that's what you're looking for, the density function. But what is a density function? Well, if you have trouble, you haven't been going through the book and you're like a newbie to these concepts, think of if you were to run an experiment over and over again, take one from this and add them, and add them, you make a histogram out of that. What would the shape of that be, okay? And this is a little bit tricky. What do you expect would happen if I'm making a histogram out of data that comes from here and here? Every time we run the experiment, we take one from X, one from Y, and add them. And what do we expect to see there, okay? What do you expect? This is an interesting question. So if this is 0, what type of...
You'd see something like a bell, maybe?
That's a good thing. The good thing is you're saying you don't get back what you started. It's not going to be a box. See, these guys right here, if you just look at X, it's a box, okay? So it's 0 to 1, and it has height 1. So, and the function is 1 over between 0 and 1, and it's 0 elsewhere. If you got 2 of these things, and you're taking one point from the X, and one point from, hold on a second. Hey, it's okay. Pretty good. I've seen you for a while. It's been busy, but unfortunately I got a class. I'm teaching a class. But otherwise, I've got okay, so where was I here? So, okay, let's do something simple here. What's the mean of this? 1/2, right? What's the mean of this? What do you think the mean of the sum of these two is going to look like? The center of this one is 1/2, the center of this one is 1/2. So what do you expect the mean of the sum would be? One half plus 1/2, right. So that would be 1. So 1 would be right in the middle. But you could get values as big as what? You could be all the way over at 1 here, or near 1, and near 1 over here. So you could get values as much as 2. Now the trick is, and this is, Lorenzo had this good idea, the question is, what's the shape going to be? Okay, and then I add these two. Well, the thing to realize is that you don't get back the same shape, okay? Because it's kind of unlikely you're going to be pulling both of them when you take the sum from the extremes, you know what I mean? Unlikely that they'll be there. More likely to be somewhere, if you have one that's extreme, it'll counterbalance with one that's less extreme or on the other side. So when you add them, you get what I mean by on the other side, right? So like one of them might be over here. You take a sample from, pick something randomly from this, and then the other one might be over here. So when you add these two, you're going to end up with something that's in the region of the one. You understand? So it's more likely. It's just you got to think about this. You got to think about this. It's more likely to get stuff in the center than at the edges. The edges require you get two that have to be on the same side for both of them to be small, for the average to be over there. So I hope I'm not making this too unclear. Really, if there's any lack of clarity, maybe you should try to just build, write a little computer routine where it's popping numbers between 0 and 1 and another number between 0 and 1 and add them, and then plot them. See how your data goes. So, what would you think? So, what is going to be the height of this thing? It's actually going to turn out to be a triangular looking thing. Okay, that's 2 over here, and this is 0. The only question is what the height is. Well, I want the area of this under this density curve I want that area to be what? The area has to be 1, right? But a triangle, we know the area is what? 1/2 times the base times the height. Well, that will be 1 as long as we keep the height at 1. So you went from this shape, just by adding these distributions, the density looks quite different. Now again, getting back to what Lorenzo was saying, if we keep adding more, if we had more, we have X, Y, and Z, and a few other uniforms in 0 and 1, we add those guys and we take the average, we divide by the number of them, then indeed, as the number gets more, like you get to 10, you're going to see a normal curve popping up on you there. It's going to look awfully normal. You'll be able to recognize it instantly. So this is sort of like you're going from this to this, and it will keep on looking more. So this is sort of amazing. You take two things that are flat boxes, and now you've got a hat function, and then you can see what happens when you take 3 or 4 or 5 of them. Now, I'm not proving anything because, we're at the end of the semester, and it turns out to prove this, you need to take a convolution or something. And, I maybe I'll do that Tuesday, if I'm motivated. But I mean, the point is to solve the problems on the test. And the problem about the tennis and the bowling, anyhow, we need to answer, do something with that. You need a theorem to be able to handle that problem. Okay, I see it. Somebody's got a chat here. What chapter? Wait, 1/2 times a half. I think you're talking about this. This is okay. You've got to add the two. You got to add the means to get the resultant mean here. That's a natural. That should be a kind of a natural thing, right? I mean, let's put it this way. What if you have this normal distribution over here and this normal distribution over here? If I add these two, what is it going to be the mean? Well, that's mean 1. This one here has mean 2. Whatever the thing is that it's going to look like, it's going to have mean mu1 plus mu2. That should be intuitive. And also, when you're talking about normal distribution, all this stuff is heading towards normal. So if you're already there with these two things you're adding are normals, and believe it or not, the thing that you get when you add them is going to be a normal too. It doesn't take 10 or 20 of those things added up to look normal. It's normal already with just 2 of them. And let's write that down. Okay, so I'm gonna erase this, but keep this in mind. If you're heading in the stat route, if this isn't a terminal course in statistics and probability, then I suggest you read this section on taking the sum of 2 uniforms. You see what you get there. Okay, it's not so simple. It's like a 3/4 page of argument to come up with this density. Okay, so what is the theorem we need to do the test? Well, okay, so if x1 is normal with mean 1, mu1, and parameter mu1 and parameter sigma 1 squared, and y is normal with mean 2 and parameter sigma 2 squared, then what? Then x plus y is going to be normal. This is the theorem in the book with mean, it's like I said before, mean 1 plus mean 2. And the other parameter is sigma 1 squared plus sigma 2 squared. Now, this is the first time I realized why he doesn't write this as mu1 sigma 1 with a standard deviation, okay? Because it's correct if you just add the variances, not the standard deviations, it's something different, right? Okay, so let's utilize this theorem for a problem. Let me find the notes for the problem. All right, okay. let's illustrate this with example 3C. And if you do this problem, you can do, you can do the one on the test. So example 3C. 3C, I don't know if I'll get through this problem if I can't write the C. But I'm trying to avoid the washout. So, okay, this problem says you have a basketball team and has a, how much space do I have up there before I run out? With a 44 game season. Now, I know there's going to be some basketball fans in my audience, and for a college team, that's like just about impossible, right? I mean, I can't imagine 44 games for a college team. The pros go what, 76 games? Somebody stop me if I get it wrong. Who knows? Who knows basketball, follows it? How long is the NBA season? How many games? 81. Okay, so and what in a college team? It can't be. I'd be extremely surprised that it's 44 games. I don't believe it. How many is a college team? Nobody cares about college. Come on, man. We just got through March Madness. Okay, so
I heard CSUN's making some news.
yeah. I forget what it was. Did they fire the coach? Got in hot water again, or what happened?
Again? And I don't know. I just heard that there was some violations. I'm like, oh, I didn't know that we were.
Yeah, but that happened a while ago. I mean, it happened big time about 15 years ago, just big time. Somebody says 33 games. Okay, that sounds more like it. I know 44 sounds like semi-pro or something. I don't know, it just doesn't sound right. Okay, so let's okay, so this is broken down. You know what? I'm going to have to erase this theorem here. But I don't want to do it. How can I rewrite or something? This is okay. Normal mu1 plus mu2 sigma squared plus sigma 2 squared. I think I've written too big or something, or I'm in trouble with the washout. Okay, so of the 44, so 26 games are against Class A opponents, and the remaining 18 are against Class B. So the win percentage against the better Class A opponents is 0.4. This is 0.4, and this is 0.7. That's the win percentage. So, what do you think W? What's the random variable W going to be here? Everybody's fine for the W, not the L, right? So, what is W? Where to put it? So W will be the number of wins. So the way it is right now, you really have two situations, okay? You have those 26 games against the harder opponents and the 18 games against the easier. And we want to know, what is the probability that you're getting more than or equal to 25 games? You get 20, in all your games, you're 44, you're getting 25 or more wins. Now, let's stop for a second. If this was all it was, you could say, well, this is just a binomial. You got one binomial for the hard ones, the A ones, a binomial for the B, and you just add them. That's all you have here. But that's not what they want you to do in this problem. They want you to model or approximate these binomials that are naturally in there by normal distributions, okay? And then we're going to add those using this theorem here. Okay, that's what they want you to exercise a little bit here. Okay, okay. This is but there's nothing wrong with looking at this and saying I know what that is. That's the sum of binomials, and we haven't talked about the sum of binomials. But here we're getting into it, but we're not going to do it that way. We're going to do it the sum of the normals that individually model this binomial, these binomials. So let's let's define two random variables. So XA, okay, X of A is the number of wins against A, and X of B. I hope I'm not in washout zone here. If I am, I overpower it with lots of ink. And XB is the number of wins. So, against the B level opponents. Now, in order to use this approximation here, I'm not going to get I need to have the we did this before. We did the normal approximation, right? So it's normal with what? The mean is NP, and the variance is NP times the quantity 1 minus P. I need to calculate these, okay? That's what I need to do. So let's make a little chart somewhere. So again, I just don't know where my washout is. So E A is what? It's NP, but how many games does A have? It's 26 times P, which is 0.4. So I need to know what that is. And I should be able to do that in my head, but I'm not going to. It's 10.4. So that's one good thing to have. And now I need to get the variance of EA. The variance of EA. Now, to get the variance, what is that formula? So it's NP, which is 10.4, times 1 minus P. Now, if P is 0.4, 1 minus P is 0.6. And that will be equal to what? 6.24. Okay, now we're done with E. Again, why am I doing this? I need that to make the normal approximation, okay? Because that's how it works. Okay, you know it's a binomial originally, and then you use the binomial mean and variance to then get to be able to interpret this as approximately as a normal. Because you need that to standardize your data. Okay, so for B, oh my gosh. Okay, B, what's that expectation? So it would be NP. How many games do we have here? 18? And you're winning this many, so what number is that? I don't know. It's 18 times 0.7. Otherwise known as, who knows what that is?
12.6.
12.6. Yeah, go ahead.
I just said 12.6.
Thanks. You're working faster than I am. And the variance, well, that would be 12.6 times 1 minus 0.7, which is 0.3. And I definitely am not doing that in my head. 3.78. Okay, we've got all the ingredients now to do this problem. So, what are we about here? Well, I've got to use okay, I've got this stuff here. So, what we need to calculate is, hopefully there's space to do it, XA plus XB. So that, according to my theorem right here, that's going to be approximately normal with what? Well, what are the two means? I have to add up the two means, right? At this point right here, maybe I should use a different color. So I have to add up the two means. What are those means? They're there, but where are they here? So I need to add 10.4 to 12.6, otherwise known as 23. Then I have to take the variance of one plus the variance of the other. So 10.02. 10.02, and we need that squared, okay, because that's what it's. Yeah, the variance is going to be signal, the sum of the two variances. Okay, so, well, okay, this is the sum of the two. Hold on a second.
This is actually a question I had on the exam also. The book's notation is of standard deviation is this sigma squared. And I'm sorry, it's square root of the variance, right?
Yeah. But can you hold on one just half second? Because I just got confused about something. Hold on. And I'll get to your question. Okay, so I have to know what the variance is. It's sigma 1 squared plus sigma 2 squared. So I don't know what that is. I should be very careful. I mean, I have to verify all these calculations. So sigma 1 squared, so that variance is 6.24 plus 3.78 squared. So the variance is what? So you got to add this stuff up, and yeah, I just suppose it's not getting the answer 1636. I'm not getting it. It's making some kind of error here. Let me just check the computations. This variance is 3.78. This one is 6.24. If I just have to add those. This says to add the variances. So if I add the variances, then I get the 10.02. Okay, so there was something wrong in my notes there, okay? I don't know why I put a square there. That's not, no, this is what it is. This is the 10.02, and this is the 23. Okay, go ahead. Can you repeat your question? I'm sorry, I had written something down stupid. Yeah, go ahead.
It's what I wrote. So we're gonna assume. So we're saying variance is this sigma squared.
Sigma squared is that's the variance. Sigma is the standard deviation.
Right. Sigma by itself is standard deviation,
Right.
Which also means it's square root of the variance.
Exactly. Right. The variance, by the way, is not negative. It's always it's positive. So I mean, the standard deviation is by definition a positive number. It can't be negative.
Yeah, and on the test, you're referring to this standard deviation, right? Like
This
sigma by itself, not like sigma squared. I want to make sure I understood that.
right. So this is the variance. Okay. Yeah. No. Okay. Good. No, that's a very good question. So in the case here, so help me out. Just make sure I can teach this. So what is, according to what we have up here, what are these numbers? Just looking at this, what is the variance?
Well, the variance of x plus y would be 10.02.
Exactly. Very good. Right. And so therefore, the standard deviation would be the square root of 10.02.
Of both of them combined, of x plus y.
Yes. Because this is x plus y. See, this is the theorem we're using.
Right.
So it's the square root of 10.02.
Okay.
When it comes to the normalization.
I understand.
Yeah, it's just the numbers are just for a second there they overwhelm me. Okay, now to get full credit on this kind of problem, you have to use the continuity correction, even though I'm not sure how much of a difference it's going to make in the final answer. But I want this right here, right? So how do we? I need to try to squeeze it in down here. So this is the probability that XA plus XB is greater than or equal to 25. Okay, that's equal. There's been no approximation at this point. But we can rewrite, now you gotta use the continuity correction. And write this as equal, strictly equal, no approximation. XA plus XB is greater or equal to what? Well, we've done this before, the continuity correction. So remember, the binomial just hits integers, 20, 24, 25, 26. So to get a better approximation, they start at 24.5. This is the continuity, but it doesn't change anything because this thing is discrete at this point. Now comes the approximation. So we're approximating these with the normals. So this is approximately the probability of what? So x of a plus x of b. Now I have to normalize. So when you normalize, you got to subtract off by the mean and divide by the standard deviation. Now what is the standard deviation here? It's a square root of 10.02. And whatever I did to this side, what I've done here is made that's going to be, think of this now as that the normal is this is the, you know, this together, this variable, you could think of that as normally distributed. Now we're standardizing it. So this is 24.5, going to equal 24.5 minus 23. So I'm doing this same thing to both sides here, this inequality. And that number, okay, so now, by the normal approximation of binomial, this is the probability of z greater than or equal to what? Now what is this? So this should be 24.5 minus 23 is 1.5 over this square root, which I don't have in my, I don't have that number, but it's just, okay, so it turns out that this number is 0.4739. I don't know where to put this, where to continue this. I guess we have this, we've already used this information. So now it's just a question of using the table correctly. So this is the probability of z, standard normal greater than or equal to 0.4739. Okay, and how do you get that? How do you do that? Just a review for maybe the final exam, but you have a standard normal. This is 0. Where is 0.4739? It's like around here. And what you want is to get this part of the normal curve. So how do I use the table to do that? Okay, somebody want to tell me? So I'm just a little, we got chats left and right. Sorry, I got caught up in there. 53 point, I think it's 33 games. You're talking about the Division I, right? Like UCLA? Okay. Okay, anyhow, so how do I get this? What do I need to do? So I can take everything minus phi of 0.47, and that will give me they'll be able to use the table. So this is equal to 1, or approximately 1 minus phi. Now I got to approximate this, of 0.47. I have that, I can find that on the table. And I did that at home, so it's 0.68. So this is about 1 minus 0.68. What's that equal to? Around 0.32. Let me check if that's correct. This is what I'm getting. It's done in the book, but they're not using the table anymore. They're doing it exactly. But if I use the table, I'm getting 0.32 for this. So why do we think that's less than 50%? Well, what would it mean to get 25 wins or more? I mean, you're going against, you've got 26 games against opponents that are going to beat you 60% of the time. So it's kind of unlikely you're going to finish the season. I mean, how do we know that this is, it can't be 50%? Because here you're not getting even close. Of course, here it's more than 50%, but it's fewer. It's 8 fewer games. So it's just the fact is, it's what's the answer here again? Like, where do I put it? 32%. About 32% of the time, you'll make 25 or more wins. But look, it's not 50% because you're quite off that pace here on 26 games on the average, right? I mean, 40% of the time you're going to win those, so you're going to lose them 60% of the time. I mean, maybe we couldn't have seen this before we did the calculation, but it makes sense. Because you're beating up on these lesser ones, but you only have 18 games where you're going to win 70% of the time. Okay, any question on this? So on the test, what was the issue there? The test, it had something to do with bowling, right? And you wanted to know when the combined score was going to be greater than or less than, I forget. This combined score is bigger than 350. So, you're going to do sort of a similar process, right? But, you have two different normal distributions, and then you find out, what's the probability of being bigger than 350? And this is some sort of subtle point there, which doesn't come up, but you don't, normally when you do a normal calculation like this, you end it. At some point, it's not realistic. The bell curve goes on forever. So it's not realistic to have bowling scores of 10,000 or something like this. So anybody know what the max score is? If you have two people playing, they're two different games, and the most they can get is 300, right? So it should, when you figure out the area, you should stop it at 600 because it can't be any bigger. But it turned out I did the calculation. It was so far out, so many standard deviations above the combined mean that it didn't factor in. But on the final exam, if I give something like this, something, but maybe if the standard deviation was a lot bigger, then it might matter that you end your area, this area here, you ended it, whatever corresponds to a 600, two perfect games. Am I right that 300 is the max score in bowling? I'm sorry, I'm pretty sure it is, unless they change the rules. Am I right? Nobody wants to admit they know anything about bowling. It's just a fad, you guys. It's going to come back. Joe said, yeah, it will come back from the dead. No, okay. Do people still do bowling or 300s? Did any of my students ever get a 300? Once I had a professional bowler in my class, and he said, yeah, he hit it like in competition like once or something. What does that mean, everyone? Big old turkey? All right.
Professor?
Yeah.
Did you say this problem is similar to 3 or 5?
No, it's the last problem. The very last problem, number 6. Because you've got two. Okay, can I erase this to explain it? You got all this stuff down, right?
Oh, I see. I'm sorry. I was looking at number 5.
Yeah, no. If you're looking at 6, you've got these two normal distributions, one for Jack and one for Jill. You got to add those, find out, and that will give. If you add them, the distribution will be a bell, but with different parameters according to the theorem, right? And then you've got to figure out what's the probability that, I think it was 350 or something, I don't know, that the combined they make more than 350. Is that right? I forget. Yeah.
I think you're correct, yes.
350 or more, that they make 350 or more. And on the final, I may put another question like this, where I'm looking for what is the probability that Jack does better than Jill. Okay, that's a legitimate question. That would involve, something different. The different random variable would be just so you know, it would be the difference, right? If x is Jack's and y is Jill's, it would be like x minus y. What's the probability that x minus y is greater than 0? You've got to know the distribution of x minus y when x and y are normal. It turns out that x minus y, you can think of it as x plus minus y. Now, minus y would have the mean just negative of what what it was, the opposite, and its variance would be the same. Okay, you just intuition. You got to sit down and think about that. Okay, if you have z and you have minus z, well, z, it doesn't really matter. Z is the mean is 0, right? But if you had something that has a mean like a half, and you go minus that random variable, its mean will be minus a half. You can still use the theorem of adding these two, but you'll have x plus minus y. Just a heads up, that I'll probably put something like that on the test. All right, let me see what I'm supposed to do. Just hold on a second. I'm getting deluged by paper here. So unless there's a question. Is there other question on the test? I don't want to disavow the exam because we only have, a few days to do it. Is there any other question? I mean, what was, were you asking about 5 or what, Max? What?
Oh no, I was just looking at number 5. I didn't know we had 6 problems on this. I thought we had 5.
Well, I hope that if I posted up 6 problems. No, 5. 5 is the joint probability distribution, right, of the discrete thing. So it's like a matrix of probabilities, and a lot of those cells that you have to fill in there are 0. Okay. Did you look at it or not, or number 5, or it is? I don't know. I'm just saying, I'm trying to give some encouragement to people who haven't started yet. Number 5, a lot of what looks like just an incredible number of calculations is a lot less.
It's the joint probability. That's what we did on Tuesday with getting the probabilities of
With the red balls and the white balls, right?
Yeah.
Right. This is a little bit different. The N1. Okay, you got 6 trans. Maybe I should just. Okay, I'm going to erase this. My board's getting dirty here. Somebody's been lazy. It must have been me not cleaning it. Okay, so what is the setting of this? How many transistors do you have? 6, right? And how many are defective? And 4 are good, right? Okay, so what is N1? What is that random variable? Just to get you guys started on this problem. N1 is what? Okay, you're looking for the defects, right? You might, okay. Yeah, Mihai.
No, so you mean N1 is which one is the first effective one?
Right, as you're pulling them out, it would be on which pull do you hit the first defective?
Yeah.
Okay, so you're going to have 6. Well, look, you're going to hit it before 6, right? Because there's 2 defectives.
So it has to be between 1 and 5.
Yes. Yes, but here's the trick. This is a little bit delicate, right? Because if you hit it on 5, if N1 is 5, okay? So let's just write down for people who are taking notes. What is N1? It's the number of draws to first defective. Okay, what's N2? It's succeeding number of draws to second defective. I just want to make sure nobody misses the subtle point, right? Because if you if you hit, so you want to know the probability of, say, it took 5 to get the first one, then you're supposed to do what? Joint probability mass distribution. So, okay, so if it took 5 to get the first one, you don't really need this second draw, right? Because you got your first one on the fifth thing, you know the other defective is the sixth one, okay? This is something that wasn't clear when the book, I took this problem out of the book, when they stated the problem, okay? Realize that if you take in 5, you don't need another a draw to find the other defective, right? So this is sort of, this probability should be 0, right? I mean, this doesn't occur. You don't make another draw. You guys understand?
Wait, you're saying the probability of 5-1 is 0, or do you mean
0
is 0?
Because this doesn't happen. This is the succeeding draws to find the next succeeding. You already know if the first one defect is found on draw number 5. That means that automatically you know the next one. You don't need to take any more draws. So you would be looking at 5, 0. This is a subtle point of this problem, okay? This is the thing where, okay, you don't need any more succeeding draws here to find the second. I'm not even sure that the author, when he wrote the problem, was aware of this issue, but it's stone clear to me. You can't. There won't be another draw if you have the fifth one as your first defect, because what's left in the bag has to be defective. You don't need it. You don't need to draw it out. You know already.
Wait, but then by that notation, does that mean you can also have a possibility of something like P0 and 1?
P,
Also, not have a draw.
No, you have to have it to get that first one. You need at least one draw. Okay, to get the first one, right? Because the fastest you can get the first one is on your first draw.
Yeah.
Right. So there's no P0. There's no, there isn't such a thing. In other words, a random variable. The first one, what do you want to call that, N1, doesn't take on 0. It's a number of draws to the first defect. That's at least 1, right? Okay, I just wanted you guys to be aware of that. Okay, somebody said the first pick being defective, so I don't want to give you the probabilities. I don't want to do the problem for you, but I think you've got it. Just be careful. Just make sure it makes sense, okay? Most of all, don't just pop into a formula here. Just make sure it makes sense. There's a lack of realism, if you're allowing 5-1 to happen, it's a lack of realism because you know that the other one, you've identified both of the defectives at that point. All right. Okay, so that was that. I mean, I don't know. I mean, should we do one of them? Maybe you want me to do so. 2, 2. What does this mean? What situation is this? You found the first defect on the second one, so you pulled out a good one, and then the very next one was bad, and then it took 2 more to find the other bad one. Okay, so that's a conditional probability thing, right? You can calculate that. You use the generalized multiplication rule. Mihai?
So you're saying P2, 2 means the second one you pulled is bad.
Right. So what happened was you originally had 2 defective and 4 good, right?
Yeah.
So your first one had to be one of the goods. Your second one is going to be one of the defects.
Yeah, but I mean in terms of like how you're pulling them, you're saying the way you are explaining it is like after the fifth pull is the bad one.
No.
Second, I'm sorry, if like if
The second pool, okay, first pool, we have 3 good, right? So you just took out a good, right? The next pool is going to be a defect. So you just took out a bad one. The next pool is a what? According to this situation. The next pool is what? It's like after you got that bad one, the number is succeeding till the next baddie is what? How many? Well, it's 2, right? So you're gonna pull another good one, and then what? And then this says, and now you get a bad one. So you really need the probability of this happening to calculate this. Okay? It's awfully quiet. I think this notation N1 and N2 is confusing. N1 is the number of pulls to the first bad one. Now N2 is how many additional pulls are needed to get to determine the next bad one. The other bad one. Okay. Am I still there? Or?
Professor?
Yes.
So for this example, we looked through 4 different transistors, correct?
Exactly, right. And the fourth one was the second bad one. Does that make sense?
Correct. And you start counting for the additional transistors, or for N2, when you get the first one, and then on the first bad one you got was N2. And then you
Right,
get
it's a
2
little
more.
complicated. Right, it's a little, honestly, it's a little complicated, the definition of these random variables, right? Because the N2 really depends on what happened to the N1.
I see.
They're definitely not independent. But again, don't fall for the thing where after 5, if you got 5, you found 1 after 5, right? But if you only had 1 bad in 5 thing, you're done, because the one that's still in the bag is bad. You don't need to pull it out and check it. It doesn't have to be pulled out. I have a quick question. Sorry if I mentioned this before, but can we clarify what criteria used for the fair coin one and with a certain? I'm looking at the chat right now. With a certain use for the fair coin. Okay, for you talk about the coin problem. So you're going to start with a Bernoulli, binomial distribution. You're going to use the continuity correction and use the normal approximation, and then you'll have to interpret your result. So yeah, and we already talked. Okay, so the large number. Well, estimate the p-value. What's the probability of getting that result or more extreme? If it's essentially 0, then the coin is biased. So I just really want to see the steps, and how you interpret the end is not so important to me. I mean, if the p-value is really small, then that means it's very significant. So that would mean that you have significant evidence against the null hypothesis. The null would be that the coin is fair. Okay, so yeah, this is just standard statistics.
So it doesn't matter if it's 95% or 99% that we're looking at.
It doesn't. No. Well, P. We mean if P is 5% or 1%.
Yes.
Oh yeah, it's still overwhelming evidence against
Exactly. So yeah, because I know under just regular scientific research, I mean, a lot of times they're just looking for the 5%. That's it. Unless they're looking at medical, like certain pharmaceutical stuff, they get more critical. But most of the time, 95%.
I thought that in science, 20% P is publishable.
Which was that?
20% P 20% is publishable.
That means the soft sciences. I'm just kidding. Don't say that. I don't know. No, I mean, it could be. I don't know. But I mean, just normally what they teach us in theory, I mean, they're usually saying 95% is that, or 5% is
that's
acceptable.
To me, that's overwhelming. Because, here's the deal with when you're doing experiments with real life data, the data is all noised up. It's fuzzy, and you can't expect to get it. It's really hard to get a p-value that's small, like that. I mean, it's like, it's like real data doesn't come from a test tube, right?
No, exactly.
So this is the first time in my life I've heard that you need 5% or 1%. I would say
Yeah.
P equals 20% paper, publishable.
Yeah.
Time to publish or perish.
No, I hear you. But so it's basically up to our discretion whether we use the 95. I mean, the 5 or the 1%.
Yeah.
Okay. Well, I mean, either way, anything over 5 is going to be crazy.
Under 5. I mean,
under 5. I meant.
Yeah.
Sorry, under 5.
Yeah.
I hear you. Thank you.
Okay. Yeah.
But I think that's what they're all asking, because that's what we're all confused on. Is like, everyone wants a finite cut number. Whereas,
what's the trigger? Yeah. What's the trigger?
Yeah.
What's the trigger before you reject the null hypothesis? Well, that trigger, is my understanding, is 20% in science. But and I'm telling you, the data. I mean, I read Scientific American, and every issue they've had something about dark matter or something like that, and they're running some experiment where if there is dark matter streaming around, then it will collide with, once in a blue moon, it will collide with something in some collector, and they're expecting to get 1.7 collisions in a year or something.
oh, really?
So it's like they want to publish, right? But they don't. The data they've collected so far it's just not. Okay, then they get P equals 30 or something, and they're so hopeful that we found dark matter. It's there. P equals 30. I mean, if to get something less than 20 in an experiment like that would be revolutionary. Especially if it can be replicated, it would be revolutionary. It's like ESP. If you did some experiments on ESP and you have P equals 20%, ESP exists. It'll be in the headlines. On paper.
Professor.
Oh, yeah. Okay.
Professor.
Oh, yes.
Quick question. For number 3 for the coin, do we use a continuity correction?
Yeah, the continuity correction. But you know what? It probably doesn't matter. I just want you to see you do it.
Right.
It doesn't matter because I think the answer is a foregone conclusion. But I mean, I guess if nothing else, you've learning about the law of large numbers or something like that, on this problem. I just want you to see it go through the motions of the continuity correction and the normal approximation of the binomial, and then look at the table or something.
Do we use symmetry? So like how we did for problem number 6?
No, because you're asking yourself, that's a very good question. It sounds like you've had some statistics. The way the coin toss is, when it says biased, it's clearly implicitly said that we're talking, does it have a bias towards heads? Okay, so if a coin, think about this. If a coin is biased, it's either going to go towards heads or towards tails, right? It's not going to be both, How could that happen? You know what I mean? How could the coin be like equally likely to be really super a lot of heads and super a lot of tails, right? It just, depending on the toss, it just couldn't happen, right? I mean, that doesn't make any sense.
I see.
It's a good point you're bringing up, but I mean, think about the physics of it. If it's biased, it's going to be showing heads more than not, or tails more than not, but not both. You can't be extreme on both,
Oh, I see. So we just get the standardized Z value.
Yeah, it's going to be Z bigger than something, right? Z bigger than something.
Oh, Z bigger than something. Okay.
Yeah, it's not absolute value Z greater than something. This is not it's not a two-tailed test. It's not a you guys have had the basic the GE stats, right? The two-tailed test. So you're kind of the problem for the p-value, the probabilities of the two symmetrical, like you said, tails. No, this is one side. This is one side. The question is, how likely, by chance, is it to get that many heads or more?
Okay. Oh, so then we have to look for the greater, not the less.
Yes.
We're not looking for the Z less than.
No.
We're looking for Z greater than.
Think about that, Max. It wouldn't make sense, right? I mean, if you have a coin that has a tendency, sometimes you flip it and it has a lot of heads, and then now it has a lot of. It's going to be one or the other. Physics of it. It can't be. It can't be exceeding. I don't know. You know what I mean? You wouldn't be thinking of both because it's got to be one or the other from the physics. It has to do with the weight distribution in the coin.
Sure, I get it. Thank you.
Okay, so let me try to, I don't want to do what I have to do here, but I've got to do I have to fill in some holes in what we covered in chapter 5. I got to actually go back and fill in something. Okay, so what I'm looking at is example 7a. This is chapter 5. And okay, so this has to do with getting the distribution of a function of a random variable. Okay, and I wish I didn't have to do this, but it's. I told you before, it's an odd thing that the stat courses that go up from here, they spend an inordinate amount of time doing this because they like to take Jacobians and formulas and stuff. Professors like to pontificate, and to me, this is not. I guess I'm not a statistician at heart. I don't like it. But this is something you have to do. So let's look at this example. So X is uniform 0, 1, and we would like the distribution of Y equals, let me think, I think it's X to the N. You want to get this distribution. How do we do this? And there's two ways to do it. You could use a formula in the book, which eventually we will do. Maybe I'll give it to you on Tuesday. But it's considered useful for us to practice the technique here, okay? Because the book does it over and over again, and the stat books do it over and over and over again. So how do we do it? Okay, so the technique is what? You're going to get the CDF of Y. And once you have a CDF, what's the technique for getting its density function? You do what? Derivative, right? So if we can get the expression for the CDF, well, then we can very quickly get the derivative and get the density. So this is what? What is this defined to be? This is the probability that Y is less than or equal to Y. And the joke is sometimes in our book, they'll put an X here. It doesn't matter. The Y, that is a dummy variable. He's not consistent with this. And so this is the probability of Y. So this is Y is X to the N. It's a substitution. And now, because I know that X is positive, I don't have to worry about absolute values here. What do I mean about worry about absolute values? Well, suppose I had X squared, and I would like to take the square root of that. This is an important thing. I think you guys understand this, but if I take the square root of X squared, and it's possible X itself could be negative, right? So what is the square root? Square root is a function, so what is the square root of X squared? It's good. If you don't know it, then we learned something this afternoon, this evening. What is it? What is the square root of X squared? I'm just talking about algebra here.
It's just X.
Well, what if you had minus 3 squared, right? What is the square root of minus 3 squared?
All positive values.
It's just 3, right? Because it's a function. You can't go plus or minus. You have to choose one. So it's 3, right? So what do we need to do in this to make this correct? We can't just put X.
It's the absolute value of X.
Yes, right. Very good, yeah. So you have to be careful. Now, this doesn't happen. This doesn't come up if you know that X can't be negative. But, repeatedly through the book, and when you take statistics, you'll encounter this situation where you're going to take a square root or some even root of something, okay? And you have to check whether the thing you're taking the root of is negative or not. It doesn't matter for cube, right? If I take the third root of X cubed, what is that equal to? Well, what if I have minus 3 cubed? What's the cube root of minus 3 cubed? It's the cube root of minus 27, right? I know what that is. It's just minus 3. So there's just, you don't get a problem there. From Devin to everyone. Okay, what are you questioning? I'm not sure. Minus 3, right, that's right. What is the question? I'm not sure what the question mark's for. Let me try to figure this out. Never mind, okay. Okay, so with that behind us, we're free to move about the country. No, I'm sorry. We're free to do what? We're free to just take that nth root. Okay. Now this is the CDF of x. This is 0 to y over 1 over n. And x, its density function just 1 in this region. If you want to do it, you could put it in, but I'm thinking it's kind of unnecessary because it's just 1. In there, and so what is the answer? Well, okay, so if I evaluate this, it's just y to the 1 over n. Now, if I want to find the density function for f, for y, so this would be, let's make sure we don't lose the track here. If I do this gives me the density function for y, but it's going to be the derivative of that. What's the derivative of y to the 1 over n? Well, it's easy. It's y to the 1 minus 1 over n. Excuse me. It's y to the 1 over n minus 1 over what? What has to be in the bottom? So it's okay. So when you take the derivative of this, it's 1 over n y to the 1 over n. So 1 over n, there must be an n under there. And this density function is for y between 0 and 1. Okay? And if it's anywhere else, it's just 0. And that's because of this. All the support for x is between 0 and 1. Okay? So that's one problem. And Ross must find this it's sort of important because he gives you 3 problems here, and they're very similar. But he must be aware that people have trouble with his manipulations, and so he pounds it into us. So what do you think the next version is? Unless I have a question, let me check the chat. So what's an upgrade problem? How can I upgrade this problem to make it a little harder? Well, you don't have to assume that x is uniform. You could say x is some random variable, okay? It's just some random variable, and it has density little f sub x, okay? So x, so you can upgrade it by going to 7b, and instead of assuming x is uniform, and just say x has f of x, its density f sub x, and get now he's going to make this part easier. Instead of n, he's going to put it 2. And you know what? We can do the same thing. We can do the similar thing. There's nothing about the earlier one that when x had a particular distribution and density are synonymous. There was nothing about that here. So let's just see. The only difference, we can go ahead and just change the things that matter. So this is x squared. And the fact is, this density could have negative numbers. X, the random variable, could take on negative numbers. So I got to be careful if this at this stage of the game. Okay, I gotta be careful at this stage of the game. Why? Okay, so because when I take the square of both sides, I get the square root of x squared. That's absolute value. Okay. Now we have to ask ourselves, what does it mean that the absolute value is less than or equal to something? Let's just review this concept from pre-calculus. If somebody says the absolute value of x is less than or equal to 3, what are they referring to? 0. What region is that? Well, between minus 3 and 3, that's exactly where x can be. If it's any bigger or any less, it's not going to be the case. So we have to think about this. So this means that how can we get this thing here? So this means that minus square root of y is less than or equal to x is less than or equal to, this is the probability, less than or equal to y to the 1/2. Okay, that's what that means. Okay. Now, what about this? Well, you can express that in terms of CDF. So this is f of x of y to the square root of y minus the CDF of that of minus y to the 1/2. And what's going on there? Well, if you want the CDF from here, if you want the probability from here to here, you take all of this stuff going up to 3 and subtract off everything up to minus 3. That would leave you with that amount. We've done this before. Okay, we've done this. This shouldn't be anything new. Is there any question on it though? I mean, I could review this with a normal curve. You want me to do that, or are you comfortable with this? Are you comfortable with this step, or should I do something with a normal curve? Tell me, because I can't read your faces. In fact, nobody's got a live face, right, on here. I mean, don't make a face. Yeah, kidding. Nobody's live today. It must be that part of the semester, right? How many people do we got? 23. That's
my computer slows down when I get on the camera, so I used to try to do it, but it kept lagging, and you were dropping off. Well, I was dropping off more than you were last time, so I just keep the camera off now because of that.
I think it's all a plot to have us all upgrade our computers. You know, it's like Zoom probably gets money from Microsoft and Apple.
Could be.
You know, the message is you need to get a computer that's faster. You need to spend more money. I don't know. I just like it's so much money goes into iPhones, computers, tablets, and I don't know what. But anyhow, so if you want, I'll explain this to you. But I don't want to, belabor the point if everybody gets it. You want to get this interval here, you go everything up to here minus everything up to here. That will leave this. Okay, so are we done yet? Or are we having fun? No, we're not having fun. So what you want to do now is take the derivatives. So what we have is this. So we need, when in doubt, take the derivative, right? So let's do it in red, because now it's the kind of like the final ingredient. So that would be what I'm looking for, f sub y and y. But that's equal to what? It's equal to this thing here. So if you take this derivative, this is f of x, y to the 1/2. Now I've got to take the inside derivative, which is 1/2, 1 over the square root of y, minus, that's the x of minus square root of y. But then this is 1/2, this is minus 1/2, 1 over square root of y. So if you're looking at the negative signs, there's one there, there's one here. Those two cancel out. So the final answer, which I don't have space to put, I guess I got to write it up here. I'm doing pretty poorly on space management today is you pull out the common thing,